Yes, hi guys. So today I want to talk about mean value and the root mean square value. Okay, now these two values are important so far as science students are concerned, okay, or engineering students are concerned, because in this case, root mean square value is important for finding out AC electrical circuits. Okay, in case of alternative current or AC electric current circuits, we have to apply root mean square value. So that is another point we will discuss later. But today I have to talk about what are the mean value of a function, mean value of of an arc, of an area, of a volume as well, okay, or of a function which is based on three-dimension figures, okay, or volume. So mean value of a volume, mean value of an area, plane area, mean value of a curve, okay, in one variable. So one variable, two variables, and three variables. These kind of figures we have to talk about. Okay, and then I'll talk about, okay, and then root mean square value. So root mean square value and mean value, these two are the topics of today's. Okay, and these I have taken okay, on the student's request. Okay, online student, they have asked me only these 4 questions. There were some more questions also. Those questions were not traceable, okay, at the moment, so I'll take them if required later. But these questions are taken from students' queries, online queries. Okay, so before taking these questions, let me clarify that what is mean value of a function and how do we find out this. Okay, in case of mean value of a curve, okay, we have to put the mean value of a curve in case of, suppose this function is y equal to fx function is given. Okay, so this value of a function fx, we have to differentiate, integrate it with respect to x. Okay, suppose y equal to fx function is given. So y into dx, integration of this from, suppose the two limits are given, a to b, or okay, any a1 to a2. Okay, so we have to take those two limits. Within these two limits, we have to find out what is the value of this function y equal to fx after integration. Okay, putting these two values in the numerator, and in denominator we have to divide it by the length between the two limits, a to b. That means b minus a. B minus a is the range or length of the that curve given, okay, within the two limits. This we have to put in the denominator. So the value of the function under the limits, whatever the limits are given, so that the total length is covered. Okay, total length that divided by the length between these two values, okay, b and b minus a. That we talk about. And then area. So area, in case the function is given in two variables, fxy, y equal to fxy. So in this case again, y into dA, area. Okay, here integration is to be taken on area. Area is in dx dy, suppose. Okay, so of a small element, then we have to integrate it within the limits given. Okay, whatever the limits of two variables are given, double integral sign in case of area, integration of area. So let me define them so that it will be clear then. So then we will apply this on the volume. So this is how mean value and root mean square value of a function. So first, mean value. What is the mean value of a function? Let me first find out what is mean value. Mean value of a curve. And the equation of a curve or a function in one variable. Function of one variable. That means a length. In this case, let y equal to fx is a function of one variable x, of a variable x. Okay, in the open interval, let me take a to b. So within this limit, what is the value of this mean value of this function? So let the mean value, so or therefore the mean value is given as mean value of this function is given by the formula is given as, let me take mean value by, this is ym, we may say capital Y, small m, this is ym, mean value of this function is given by integration sign. Here limits a to b, within these two limits a to b. Here it is y into dx. This y function is given here, divided by limits. Here the limits, we have to take the same limits a to b, and here only this dx with respect to the variable given here. So dx, this is length, but it will comes out to be, now it will be a to b, let me take fx here into dx, divided by b minus a. Here this b minus a, because this is differentiation of this, integration of this will be x only, then put the limits b minus a. This b minus a represents the range of the length, or the length between these two variables, these two values, okay. And here b minus a represents the length between the two values, between b and a, or b minus, between a to b, between the values a to b, or this is b minus a. This is the length of the curve, you may say. Or suppose there is a wire given to us, then we have to find out what is mean value of that wire. Okay, so we have to put the function in terms of that variable, or that function of the curve given, that is in the numerator within the same limits a to b. In the denominator we will take the same limits but length of the value. So this is in case of one variable. And mean value in case of a plane area, let me take that also. And mean value of if a plane area, or if I take function in two variables, let me take, that means area. Okay. And second point is mean value of a plane lamina. Okay, if this plane lamina is represented as area A, okay, and if the function of the plane lamina is, let me take here, because x and y we have taken the two variables. Okay, so let me take z equal to fxy. Okay, is a function of the, or function of the area, plane area of the plane area in two variables, x and y. Okay, so in this case, what is the then mean value? Therefore, mean value of the plane area or plane lamina is given by, let me take, this is mean value Zm, mean value of the function. Here we have to take the area interval. This integration is on area, and this is fxy into dA. Let me take area here, divided by, again, area and interval on area given to this, and this is dA only, the total area in the denominator. This is area here, it will represent as, let me take again fxy. Now this area is in dx dy, the two variables, so we will take these two variables here. Okay, and divide, and this is dx dy divided by area, total area. Here this is area of the given plane. Okay, plane lamina, the area of that is to be substituted. So area, length in the denominator. Previously it was length in the denominator, now it is area in the denominator. And in case of three variables, if it is the volume given, then the volume we will substitute in the denominator. So after calculating this volume within the same limits, suppose the action by limits are also given, those limits will be substituted here. And within those two limits, we have to find out what is the mean value of the area, plane lamina. Okay, so this is in case of mean value of plane lamina is given by this in the second equation. We take this as second equation here. Okay, so plane lamina, mean value of the plane lamina. Now let me take what is the mean value of a volume of a solid. Okay, in three dimensions or in three variables. So if I take mean value of a solid or applied on a volume. Now third point here, what is the mean value of a solid or on volume? On volume, here we have to take the volume. That means function is expressed here in three variables. Here the function is described in three variables. In three variables, x, y, and let me take z. So let us take the function or any function may be represented by u, by v, or by other thing in terms of x, y, and z. So let me take here capital U is equal to f, x, y, and z. Or this is v. Let me take this is the volume here. Let me take this is volume capital V. V is equal to fx by z. Okay. Or if I differentiate volume, because in the denominator we have to find out the volume here. Okay, so this therefore mean value of this volume, this Vm equal to, therefore mean value of the solid is given by Vm is equal to triple integral sign here on the volume, applied on volume here. This is fx by z into dv divided by volume integral, and here it is dv only, the volume. So this can be further explained as applied on volume, three variables x, y, z. Okay, this is based on x, y, and z. This is for z here. So this is fx by z dx dy dz, right, divided by, here we will take the volume. This is dx dy dz only, or we can take the volume. This is dx dy dz. Our total volume will be in the denominator. This is upon v, we can write this is triple integral sign fx by z, or fx by z dx dy dz divided by volume. Complete volume we will calculate the denominator divided by volume. So mean value of a solid. In this case, this is the third equation. Now, how to express the root mean square value, okay, R.M.S. value of a function. Now, similarly, we have to extend this in case of, okay, now root mean square value, second topic of this. Then we will take these two illustrations on mean value as well as on root mean square value. So before that, let me take what is the root mean square value, the second topic here. The root mean square value of a function. How we represent it, that is the point. Okay, so first let me take the first point, first case of this. I mean, the first case of root mean square value is R.M.S. value, root mean square value of a curve or of a curve in one variable, variable of one variable. This is of one variable Alright, let me take here y equal to fx. Let y equal to fx be a function of, this is of a length of an arc or length of a curve given by this, be a function of x by, sorry, here x only, a function x only one variable. In the between the limits, the same thing. Between the limits, a and b, this open interval. Again the same thing. What is the root mean square? Therefore R.M.S. value, root mean square value of this y by, let me take R.M.S. here, is equal to, this is single integral sign fx here or y into dx. This is y square here. The same thing we substitute, but here y square we have to substitute. So square root of this whole value divided by single integral, this is dx only. Okay, limits, let me take a to b, the same thing. Only square root of this, but here we have to square this value, y square. So it must be y square into dx, not single y. In case of mean value, there were only y. Here we have to take only y square. This is the only difference. In case of, and then square root, the square root of this value. Root mean is square value. The root mean, what is root mean of a square value? We can just define it. It must be a square only. The root mean is square value of a curve. In this case of an length of an arc here, we have taken the function y in one variable only. In this case, limits are taken. Here b minus a again. Same thing, denominator is the same. Only numerator is changed here. Okay, so this is a to b y square into dx divided by b minus a again. The same thing. After solution, whatever comes out, that is the result of this. This is the first case of root mean square value. Root mean square value formula is for curve, length of a curve is given by this. Let me take the second case. Okay, so what is the second case? Second case of root mean square values. That means, what is root mean square value of a plane lamina, of area of a plane lamina? So second case in part second. R.M.S. value or root mean square value. Root mean square value of a plane lamina or applied on area. Let us take y equal to, again, fx by, okay, of two variables. This function is of two variables, x and y. Okay. So what is the root mean square value here? Therefore, R.M.S. value of y is equal to, this is the square root of, here it is limit, let me take within the same limits a to b, sorry, here it is area, so we have to apply it on area, a, let me take area, apply double integral sign. Okay, so this plane lamina here in this case, this is fxy square here, so fx by square, okay, into dx dy, or it may be y square. Let me write here y square, first y square, so it is y square into dA, it is y square divided by the same area, here it is only dA, it will be whole square of this, that means fx by whole square. We can write further square root of, this is double integral sign, area A, this is f square xy dx dy divided by, this is again area integral, this is area dx dy. This is second root mean square value formula. This is square root f square fx by dx dy upon this. Well, this is for root mean square value of plane lamina. In this case, f square is there, y square or f square. Now here function is in x and y of two variables x and y. Okay, so this is the second case of root mean square value. Now third case, which is of a solid or applied on the volume, if it is expressed in three variables f, x, y, z. Okay, so case number third, so root mean square value of a solid, okay, applied on the volume. Let here y, or not y, because y is the variable expressed here. Let me take here u, capital U equal to f, x, y, z. Here three variables are there. The function is here on applied on volume. Okay, so because three dimensional figure it will be there, so volume. So this is so root mean square value of u. Therefore, R.M.S. of u, or R.M.S. value of u, sorry, this is root mean square value R.M.S.V. Let me write here. Let me write it in short. So it is R.M.S.V. of u will be given by square root of. Now this is triple integral sign. F square x by z. First it is u square, then dx dy dz. Write directly. This is volume integral. Triple integral sign, volume integral, and dx dy dz only. Directly. This is square, only square. Same volume in the denominator. In case of root mean value also, we were taking the same figure here. But in case of root mean square, this square must be there. Then square root of the whole. This upon this. This is numerator upon denominator, or square root of that value. Okay, so that we will consider one by one. Now let me take these questions which are based on mean value and root mean square value functions. Okay, or these formulae. So the topic of today is mean value and root mean square value that I have described. Now let me take the questions one by one. First question, what does it say? Now question number one, let me take simply. What is question number one here? Only 4 questions I have taken so that the topic can be very clear. Okay, so let me take question number one here. This is second. Question one say a particle moved from rest, okay, with constant acceleration. Now here acceleration we will take consider as a, or acceleration a, let me take, so that in any interval of time, from the starting point, the space average of the velocity is 4/3 times of its time average. Okay, it says the space average of the velocity, and time average of the velocity. Space average of the velocity and time average of the velocity is given by is 4 times. So this, space average of the velocity is 4/3 times of its time average velocity. That is the point here. So let me take what is the function here or question given. Question number one says that a particle moves. What is given to us? Given here a particle moved from rest. A particle moved from rest with constant acceleration. Let me take acceleration. Let me take acceleration is equal to small a acceleration. The first part of this small a or capital A that can be taken. Okay, small a, and acceleration we have assumed that is taken from rest with a constant acceleration is given, so that in any interval of the time from the starting point the space average of the velocity. So if I take Okay, and if s is the distance traveled, time t is the time traveled. Okay, so let me take, let t is the time, t is the time, okay, from starting, okay, is the time taken for traveling, t is the time, and s is the distance, small s is the distance, equal to distance traveled after time t. Any interval time t we have taken after time t. So as we have taken t a. Now what are the equations of motion? Okay. So equation of motion are given as s equal to ft or at. We have taken v is equal to. Okay, so let me remember those. There are three equations of motion we know about. What are those three equations of motion? Okay, so let me talk about them. So first is v square equal to twice as. V is the velocity here. A v is the velocity. And s equal to half at square. Okay. And first is v equal to at. So there are three equations of motion. Therefore, the three equations of motion. The three equations of motion, in this case velocity in space of motion, are, first is v equal to a into t. This is the first equation. Second is v square equal to, okay, first is this s equal to half a t square. This s is also there. This is the third one. Half a into t square. This is the third one. And second is v square equal to twice as. This is the second one. So these equations of motion will be applied here. So let me take them one by one, and then we will substitute these values in terms of s. S is the traveled distance, s equal to half a into t square, and v square equal to twice as, and the third is, this is from beginning, v equal to 8. Okay, the velocity given, last velocity. Okay, we have not taken any initial velocity. This is velocity here which is required. Velocity is 4 upon 3 times space velocity. They say the space average of the velocity. So first mean space, average space we have to find out is twice. So only mean value of the velocity we have to find out in space, and the time average. Okay, what's time average we have to find out. Let me take what is the velocity, space average of the velocity. So therefore, now solution we are finding out. These equation of motion can be given, or we have taken them. Okay, s is the distance here, t is the time taken for traveling, and a acceleration is a. All these things are given. Now solution, let me find out what is the space average velocity. So space average velocity and time average of the velocity. So that we have to find out. So therefore, mean value, mean average or mean value of the space velocity. This is space velocity. Space velocity. Okay, is given by. Now let me take the space velocity in case of distance. Okay, velocity s 0 to, take capital S here. Now this is v into velocity into ds, because this is in terms of s distance. Okay, this is vds divided by 0 to s into v into ds. Sorry, only ds. Sorry, what I'm writing here. I've discarded even then. I'm writing this. I'm sorry. ds. This is only s, because this is integration of this is only small s. This is small s here. Then substitute this value. It will be capital S. It will give us 0 to s. We are substitute from the given equation. But before that, first V is this one 80, or let me write here 80 0 to S A into T here. If I take this in, this is in S terms of S here, then not in terms of T. Let me take the second one. So we have to take this S in terms of S different. This is square root of twice A into S into ds divided by only S. What integration of this will be small s, then putting the limits small s, putting the limit 0 to capital S. That will give us, okay, and in this case, this is under root S here. Under root twice A, let me take outside. Constant 0 to S, this is S whole power half into ds divided by capital S. This is capital S only 0 to S. So S limits we have substituted here. So let me write now here. Okay, and these three equations of motion, let me write here. Acceleration is A, V is equal to A into T, the first equation of motion. Then V is equal to twice AS, second equation of motion, twice AS. Third one is this S equal to half A into T. So these are three equations of motion we know about. Okay, then, and this first one we have applied, so this second one we have taken here twice AS, under root twice of AS. This we have applied here. Now let me further integrate this. So this will give us, let me write here. Therefore, your solution we are finding out. So, mean velocity we are finding out. Velocity in space, let me take mean space velocity, or mean space velocity is equal to this, this under root twice under A divided by S, capital S, this one. And this is integration of 0 to S. Okay, now let me integrate this. It will be S whole power 3 by 2 upon 3 by 2. Limits 0 to S. Capital S, this is small s, let me take. And this is capital S. So it will be